All right, welcome everybody to our traditional VSA webinar, and it's my pleasure to welcome Fritz Sommer, who will talk about his recent work. So without any further delay, so Fritz, the floor is yours.
Okay. So good evening, good afternoon, in whatever time zone you are. I'm very thank you, Evgeny, for inviting me. It's a big pleasure to present, and I see here a lot of familiar names in the attendance, and it's great. I mean, David Rowland, I can't believe it. Hello. Okay, so let me just start. So let me make this. Can you see my full screen?
Not yet.
Okay. Oh, sorry, I did not. Yeah, little detail. Let me share my screen. So sorry about that.
Yeah. No. Yes. Now. Yes. Now we see it.
How can you see it? Okay. Yeah.
Yes.
Okay. Yeah, so the title is Computing on Functions Using Randomized Vector Representation. This is kind of to hide the title a little bit, that it's all VSAs, and most of you are very familiar with that. And so, okay, yeah. So let me start with my collaborators in case we run out of time. It's Parks and Frady, who is with the Neuromorphic Computing Laboratory at Intel Labs in UC Berkeley, Dennis Gleiko, UC Berkeley right now, and also Luleå University in Sweden, Bruno Olshausen, UC Berkeley, and Chris Kim, who is a PhD student of Bruno. So if you think about the principles of neural coding, there's kind of two different approaches to it. One is really kind of data-driven, often using unsupervised learning. And the idea is often to kind of squeeze out redundancy of a signal. You know, if you have pictures or sounds, there is redundancy in the signal. And so the idea is very much source coding. And the algorithms can be, you know, principal component analysis, independent component analysis, and then more sophisticated things like manifold learning, also predictive coding. And opposed to this is our neural encoding mechanisms that just use simple randomness, like, for example, random projections. You have a layer of neurons that is just connected to the input by a random matrix. You have a recurrent network with often random weights, like in reservoir computing. And also more recently, there is connections between compressed sensing, kind of a principle invented in, or named at least, in signal processing, which also uses sparsity in the signals and neural networks. And yeah, and I mean, what we do in vector symbolic architectures is that we represent things like symbols, for example, by randomized neural activity vectors. And I will come back later that, of course, some of this can then be computed in a network that has actually some random weights in it. And so this slide, this audience almost does not need. So this is just the one slide introduction of a vector symbolic architecture. So one important principle is that you encode things like symbols by random vectors, and you can formalize this basically by this. So you have a probability distribution for each component of the vector P of Zi, and you then and it's a factorial distribution. So these symbols are drawn independently for each component. And this is basically how you assign a symbol to a representation vector. We all know that. There is then, of course, the algebraic operations like the bundling operation, addition. There is a binding operation. That's all known to you guys. You can use this then to reason with the symbols and to form actually data structures, variable data structures that contain sets of symbols in a particular structure, like in a tree and so on. I will not go into that, but all I want to emphasize here is that once you start to use this encoding scheme up here, this means for the inner product, and I just write this here as the Z, so S, this should be S1, not SC, I don't know, that's a typo here. So Z of S1 and Z of S2 are representations of two symbols, S1 and S2. And this is just how I denote the inner product. It's one of the vectors transposed. And in general, if Z is a complex vector, I take here the complex complementary. And one thing to note is if you have actually an encoding like this, which is IID, then basically this inner product is proportional just to the expectation value under the P of C, under this encoding distribution of the product of two of these components of the vectors. And that's kind of important. This is what will be used. And then, of course, also you need cleanup, which is usually done by constant addressable memory. Then that is kind of the machinery that we use in vector symbolic architectures. So far, so good. Nothing new here. And on the next slide, okay, there we go, is just a little other kind of take on standard VSAs. And so basically what we use in, for example, symbolic reasoning is that, two symbols that are different have also an inner product, which is rather small, whereas actually if the symbols are the same, maybe some noise on it, but then you want that actually the inner product is quite high, is, for example, normalized to 1. So what you ideally want for symbolic processing is actually a kind of a chronicle kernel between. So if we now kind of just take this inner product as a kernel function, what we would like is to have here the chronicle function between S1 and S2, meaning that if S1 equals S2, we would like this inner product to be near 1 and otherwise very small. We all know with just this randomized pseudo-orthogonal encoding scheme, we cannot really get it exactly to 0, but we want to get it close to 0. And this indeed also is actually nicely the case. So you can actually show that actually the difference between the inner product of such an encoding scheme and the ideal chronicle kernel can be made arbitrarily small if you just make the dimension of the vectors large enough, which is kind of this concentration of mass phenomenon. And so this is the perspective that we take, and then we just go through one step of generalization. Before we do that, I will just here review without proofs or anything, some results from functional analysis that we are using. I mean, if we talk about kernels, kernels is a very old idea, has been basically introduced in the turn of the last but one to the last century in the group by David Hilbert. And so so what will be important for the following is basically a positive definite kernel. It's just a definition. So whenever a kernel is called positive definite, whenever actually if you have a set of points And then the matrix that you can form by just putting in here pairs of points has to be positive definite. And once the kernel is positive definite, we can use this theorem that basically all inner product kernels are positive definite. So as soon as you write actually the kernel function as an inner product, it is per definition positive definite. And then an important theorem is really the Aron-Sine theorem from 1950. Each positive definite kernel defines a reproducing kernel Hilbert space, and we'll later come to this, that if we now extend our kernel definition away from the canonical kernel to a more smoother decaying kernel, then actually we get these function spaces that we can represent with our VSA vectors. And another thing which is very important is the theorem by Salomon Bochner, which is that each kernel which is positive definite is the Fourier transform of a positive definite probability density. So this is kind of here the formula for the Bochner theorem. It just means whenever you have a positive definite kernel, it can be written as a distribution in Fourier space as the Fourier transform of a probability density in Fourier space. And this is very important because this integral can then also be written as an expectation over this function P of omega, where you basically just have here these two factors here. So the expectation of basically here these two factors equals then the kernel at x minus y. So this is what we will use. I just put this up here that you know this is no new inventions here in terms of the mathematics. This is kind of very well explored ground. You know, this part of functional analysis then has been taken up by the kernel machine learning community in the early 90s, in the 90s. But a lot of this work is much older. And it starts really in the early around 1900. Okay, so now we basically just take some of these things that I just mentioned here, and we generalize the vector symbolic architecture a little bit by introducing first now an encoding function which is locality-preserving. And so this is a function that actually maps a variable from a low-dimensional manifold. Here it's just the line of the real numbers to a vector, which can be complex valued, can be over c to the n. And such a locality-preserving encoding function is a Kernel Lppe. We call it Kernel Lppe, which means it induces a similarity kernel in with the following requirements. So we take our function f. We can now encode two different values, and this should, for large n, converge to a kernel. And the kernel, again, and the convergence should be fast. And we can, actually, other people have shown that it's actually exponential in the dimension of these vectors. So it's as fast as we know it from the canonical kernel for the standard VSAs. And the kernel function is now not the canonical function, but is now usually a decaying function. It doesn't need to be monotonically decaying, so it can be the sync kernel. It can, be 1 for here the argument being 0, and then it drops down and it can wiggle a little bit and become smaller and smaller as actually here the argument or the difference between the two vectors gets bigger. And basically with this definition, you need just one other definition. We call such a kernel locality-preserving encoding method compatible with a VSA binding operation that I, in general, here denote just by this little circle. If actually this equation here holds. So in other words, if you add here two numbers on the real axis, you can also write this as the binding here of the encodings of the individual numbers. And with this, we can now define what we call a vector function architecture. And basically what this is so there is a kernel locality preserving encoding function. And that means now that you can actually form functions of this type, which are just weighted superpositions of the kernel function at support points. And these are actually the functions that can now be represented in the VFA. And how are they represented? They are represented here basically. So in this definition, you can just rewrite the kernel by the inner products, by the inner product representation of the kernel. And then the vector that actually that then represents the function f of r is just the weighted superposition of the encodings of the support points of this particular function. So in other words, if we have a vector, a VSA or VFA vector, yf, then we can evaluate the function at a point r by just forming the inner product between yf, this function representing vector, and the point representation of this point r where we want to evaluate the function. And that's basically also, we have now a VSA, but the VSA can encode points on this manifold, and it can encode functions. And the functions are of this shape. So in other words, the kernel function, which is defined by the locality preserving encoding mapping that we use, determines also the function space that can be represented by vectors. And now, what are the properties of this vector function architecture? So as I already said, one of the properties is that you can point evaluate the function just by taking the representation of the function, multiplying it with the representation of the point where you want to evaluate the function. Then you can also, but now you can apply the entire algebra that we have in the VSA. So you can you can add functions by just adding their vectors. You can actually shift functions by just binding them with a shift vector, which is just the representation of the shift value. And importantly, you can actually form a function convolution. So you can actually form a vector, which is now the convolution, which represents the convolution of two functions f and g, by just binding the representation vectors of the functions f and g. And then, yeah, in addition, you have the overall similarity between functions. It's just given by the inner product between two function vectors.
And Fritz, do you mind if I ask a question?
Sure. Yeah,
understanding. I don't understand or didn't get what you start with. What is the you initially define this function, but then you use the kernel. Is it that you have to assume that kernel is given? Is that what you start with, or?
So basically, we start with a locality preserving encoding function. which defines then the kernel. So the starting point is a function that goes from points on the manifold to the representation, to the vector space of representations. And once you define this f function, the inner product for large enough dimensionality of the vectors converges to this kernel function.
I see. Okay, I got it. Thank you.
Yeah. Are there other questions now on the more general setup? I mean, this is the general setup, and okay. Just interrupt me. Yeah, sure.
Yeah, I think this is carrying on from Gregor's point. So you're saying that you can represent both points and functions, and that the representation of a function is essentially a weighted sum of points.
Right.
So does that imply then that if you have just one point, that also is inherently a representation of a function? It's just that
Correct.
it's a...
Yes,
yeah, okay.
Correct. And this is the reproducing kernel Hilbert space property. So that's exactly right. So the kernel itself is also an element of the function space.
Right. So that if you've only got one point, but you and it's equivalent to a function, then the function it's equivalent to is essentially the similarity function that's baked in via the locality preserving encoding.
Yeah, I mean, think of the representation of a point. It's like a band limited delta function, right? So I mean, basically what
something like that.
Yeah.
Okay.
Yeah.
Okay. Thank you.
Yep. Okay. And so this is kind of, so now you might ask, okay, what are actually, what are now locality preserving encoding methods that we can use here and that kind of fit the bill? So here's one. And this is really something that Tony Blade introduced a long time ago. It's this fractional power vector method. And so the idea is the following. And Blade introduced this in his thesis in the early 90s paper. So again, you create. So it basically is an encoding method that uses a base vector. It uses one random vector, which is drawn from a distribution POC. And I will come back to that. What this distribution POC will later become very important if you want to shape kernels for different purposes. And he basically used it for encoding integers by just using bindings. So basically he encoded an integer I just by basically exponentiating the z by the integer, but with respect to the binding operation. So in other words, he just took I times the base vector and bound it. And this is a scheme that then later was extended from integers to real values. And we call this here in reference to the fractional power vector, we call this fractional power encoding. And the idea is the following: you basically can encode a real number or as a real vector, we'll come to that later, by just exponentiating this base vector by r. But what exponentiation means depends now on the binding, because you want to do kind of this, but now not for an integer, but for a real number. Okay. And this has been used before. This has been used, I mean, Blade used it also. So the easiest way to understand this exponentiation is for the Hadamard product, where it just becomes component-wise exponentiation of the base vector entries. So if you have a base vector, you can just, and your binding function is just Hadamard product, then the encoding of a point R, Hadamard product is just take the base vector, exponentiate each component of the base vector individually by R. And Paxson has used this around 2018. Of course, the much older way of the FPE is with circular convolution, and that was first used by Blade, and then later also in the Elias Smith group. Brent Comer used it in his PhD and so on. And so what you do here is basically you exponentiate with respect to circular convolution, and you can then do that by using the Fourier transform and basically do this component-wise exponentiation on the Fourier transform of Z and transform it back. So that's basically how you do this practically. And then a third way, a third binding method that is also interesting to consider is this block local circular convolution that we proposed in a 2021 paper. Basically, there you have vectors that are structured in blocks, and you do then circular convolution just for each block. And with this, you can actually get pretty sparse representations that represent then the real number R. And so this is an example where you have here blocks. You have 1, 2, 3, 4, 5 blocks, and it's just a one-hot representation in each block. And then if you actually shift this by 1, you get a representation which is again just block. I mean, it's the sparsity is the number of blocks. Basically, you have one non-zero component for each block. But you can see if you go here in between, then it becomes a little bit less sparse, but it is still quite sparse. So this is, if you continually now change the exponent here, you see how the L1 norm here goes a little bit up, and at the integers, it comes down here to the lowest values. So these are just kind of different ways how you can map now these vector function architectures to representation vectors and also to hardware and operations. And which one is the best, of course, depends on kind of your hardware, your backend, what you want to do. And I mean, yeah, in this case, you have kind of these phasor representations with the Hadamard binding. Hadamard binding doesn't make too much sense for VFA if you keep it real. So you really want to have complex vectors here. If you want real valued vectors, you can do the circular convolution. This was done in the Waterloo group. And if you want the vectors to be real and sparse, then you can actually do what we proposed here. And in each case, you can you can build a vector function architecture. So I will now, in the remainder of the talk, be quite agnostic of the back end and just tell you a little bit what you can do with the VFA, but think of these things as different ways how you can implement them. Okay.
Fritz, can I ask
so now, yeah, go ahead.
Can I ask a quick question about the limitations of the different representations? So with the Hadamard product binding, so if you look at Penty's binary spatter code and the MAP representations, which are effectively bipolar representations. Tony Plate made a comment many years ago pointing out that effectively those could be interpreted as phasor representations, but where the phase has been discretized to just 2 values. Right. So, and also, I suspect that also relates into the self-inverse property, because essentially, you know, it rotates pi radians on each product. So you can only go, you apply the product twice and you end up back where you were to begin with. But given that that's discretized phase, I'm presuming that means you can't do fractional exponentiation with those binary representations. Is that true?
Yeah, so I mean, this is true. I mean, what you can do if you want a kind of binary representations, what you can do is kind of this, if you do this block circles representation, then you have indeed binary block representations. But also here, if you now exponentiate by something which is not an integer, you actually get here non-binary representation.
Yeah,
so I think it's fair to say, I mean, all these locality preserving methods using fractional power encoding do not really work with totally binary representations.
Yeah, although it was not the actual representation per se, but the discretization of the phase to exactly 2 levels, whereas in the block representation, you've got it's not a binary representation of the phase.
Yeah,
it's spread over the 10 bits or whatever.
If you decide that some integer resolution is good enough for you, then you can just make big enough blocks and work perfectly with binary representations. But this is the condition.
Yeah, I guess the question I was heading towards there was, if it's the case that the self-inverse product property only comes with having phase discretized to 2 levels, does that then mean that essentially when we're talking about exponential fractional exponentiation, that we're ruling out using that on the algebras with the self-inverse property?
There's a self-inverse, but it's not. I mean, you also have a self-inverse with phasors that are not discretized, right?
Okay.
So that I think it doesn't touch the self-inverse.
Okay, yep. All right. No, so that was just a speculation. Okay, that's good. Thank you.
Yeah, thanks. Okay, so now let me just go a little bit through the consequences of this and end up with some examples what you can do with this. So the first thing is, so now let's look in the VFA representation space. What do we see? What kind of vectors do we have here? And I already started to explain this. So one important thing is that if you use a fractional power encoding method, that this base vector is actually unitary with respect to the binding operation. So you basically want the base vector to be contained in this set that I call here a bind, which is the set of vectors that if you bind them with another vector, it doesn't change the norm of the other vector. Okay, so that's kind of important. And then in this case, it's kind of clear. So you have now the base vector. If you just take the base vector and you exponentiate the base vector, this gives you then this orange set here in the space of VFA vectors. And these are what I call the point representations. But as was already said, the point representation is just kind of one kernel function centered at one support point. Okay, so, but this is kind of the PC is the point representations, and then the function representations, or I should say the composite function representations, probably here to be exact, is this green set, and these are the superpositions of point representations. You have other vectors here, like here in the white, that have no meaning with respect to this fractional power encoding method, right? So there are interpretable vectors, and they lie here in this symbolized circle. And of course, this is not a circle, but just to be clear here, there will be vectors that have no meaning, And so for that reason, also decoding will become an issue, right? So if you get noise in the VFA computation, at some point you also might want to actually read out or find actually the closest vector, which is really here in this circle, to some vector that is a result of your computation. It's just something to keep in mind. The next illustration here is you can now, just by changing the kind of the phase distributions of your base vector, you can create different kernels. So you can, for example, if you just take the rectangular phase distribution, phasor vector with a fully flat phase distribution, then you get the sync kernel. But you can choose here other phase distributions and you get other kernels. You get some kernels that are pretty close actually to Gaussian kernels. And you get here all kind of other shapes. And of course, in all of these cases, if the dimension is high enough, and this is here the dimension over actually the distance between the inner product and in the exact kernel, it kind of goes down exponentially in the dimension. You can also actually get periodic kernels. So if you take a phase distribution which is kind of discrete, like here, then you actually get a kernel which actually repeats. And that also was pointed out by other people before, but here, so yeah. And another thing is also you can now encode more than one dimension by, again, using just the binding operation. So you can choose different base vectors, 1, 2, and I mean, for each of the dimension, and play this exponentiation trick then for each of the base vectors and just use binding to combine this to one vector. And then you can actually, encode here a vector, and again you can kind of shape the vector. So, for example, this is a kind of a vector which is kind of the 2D Cartesian sync function, basically. So it is a band limited flat distribution in Fourier space, and you can then see how actually, if you represent this in a finite dimensional VFA space, how actually the convergence is to that kernel, and you can again see that this converges exponentially. And you can also ask, well, what is actually the error within the bandwidth versus outside the bandwidth? And the good news is outside the bandwidth, actually here, it goes, it is, the power is actually smaller. So it does not violate the bandwidth. I mean, it almost keeps you in bandwidth if you actually take a finite dimensional vector space. So that's kind of nice. And you can then also use this to create hexagonal kernels. So if you, for example, take the hexagonal sync function, then the power spectrum looks here like this hexagon, and the corresponding kernel looks like this. You can create all kind of grid kernels, Cartesian grid kernels, hexagonal grid kernels, and you can here really go into psychedelic land here. I don't know, but always keep in mind that one is, so the blue plots here are just the phase distributions of the base vectors. And note also, if you want to create a grid, then actually so let's say a 2D grid, so you need two base vectors, and then the distribution of the two base vectors cannot be factorial, but has to be really dependent in 2D space. And for example, if you actually sample them to lie from this grid from this grid distribution in phase space, you get a kernel that looks like this. if you use here this a distribution where the base vectors are sampled from this phase distribution, then you get this grid and so on. So you can see how here different phase distributions of your base vectors correspond to different kernel functions that you can construct. Now I come to the decoding. So in the paper, we also described that basically the point representations are isomorphic to a one-parameter Lie group or a path. So namely, you can take the base vector z and you can now exponentiate it by all by different values, and this kind of gives something which is has the topology of a path in a Lie group, basically. So you can think of these things like lining up here. As you change beta, you kind of go along. So this orange set here has really a structure to it, and for decoding now, for this problem that I described before, where you really say, okay, my computation gave me here a vector, but what does the vector mean? I want to denoise it. I want to for example, decode what actually is encoded. You can either do something that people often do with attractor networks. You can form a kind of a line attractor. But this is expensive. A cheaper way is really to just use a content addressable memory of points and to store closely enough spaced points on this path in your associative memory. And then you can actually just use kind of a second step here. So then in the first step, you determine the closest match in your associative memory, which is just one of these points. And then where exactly you are around this point, you can determine here by a quite simple second step, which needs no extra circuit. It's basically also, it just uses the FPE circuit to compute this. But so what we suggest here is actually the decoding can be done for single point first, and it's done in this two-step fashion. And the advantage is that you don't really need to form a line attractor that actually contains all the points that are produced by the FPE, which is still a principal question if this is possible. But even if it's possible, it's rather expensive. And what we say is, no, you can take a point, you can use a usual, Hopfield network or something, store these points, and then do the fine detection by the second circuit that doesn't need an attractor network. And the interesting thing is you can also use this to decode functions. And the functions are then decoded term by term, and you will start, of course, with the terms that have the biggest coefficients in this sum representation of the function. But it shows here that you actually can get a pretty good cosine similarity here, even with so let's see. Yeah. So what is what here? So yeah. So the different colors here are just different vector dimensions, and this basically shows that the cosine similarity is pretty close to 1. So you actually can do that. And I think for practical purposes, this is quite important. Okay, and so now let me just end. Let's see, how are we doing? Well, we are fine. So yeah, I will now just go quickly through 3 kind of example applications, what you can do with it, and then sum it up. But of course, you can already see you can now basically do everything what you can also do with kernels and kernel machines, and that's very interesting. I will come back to this in the summary. But one thing that actually Paxson has done is now to represent actually images by in a VFA as functions, basically. So he basically takes the image and then just encodes the different And this works well for sparse images like here, where basically only the points here in the A are actually non-zero, the other guys are zero. And then you can actually encode different letters by VFA vectors like this. You can store a scene, or you can represent a scene by the superposition of these vectors. And you can now also apply transforms by convolution. So you can basically form a kernel, which is periodic, so that you have here periodic boundary conditions. So the F that actually goes out here comes in here, and that's kind of convenient because it keeps the power in the image the same. And you can then do manipulations like different translations of the image also just by the binding operation as advertised before. Then you can also do more traditional kind of kernel things. You can just do a kernel density. You can approximate a density by kind of a kernel function. And there we basically just implemented, some kernel method that was described in another paper. But you can also, what you can see here is that you can actually approximate functions of this type pretty easily. An interesting thing is also if you ask now, what is actually the error that you get for a certain sample size that you actually use for the kernel density estimation. And then just the interesting thing is here that you get these plateaus. So in other words, if your VFA has a rather small dimension, you actually don't need more samples than, if you're on the red curve, you're good to go if you're basically here. You can't even use more samples. So there's this nice property that if you kind of know that you are limited in sample size, you can also limit the dimension that you actually need for the representation. And a similar thing is also true for actually nonlinear regression problem, where you also see kind of these plateaus here. And with this, let me just sum it up so that we have a little bit time for discussion. So what I basically showed you that actually a combination of a VSA with what I call a compatible kernel locality preserving encoding method forms a VFA, a vector representation of a function Hilbert space, basically in which the vector operations offer function manipulations. So you can do point evaluations, you can do integration, addition, shift, convolution. And in particular, the convolution is interesting because you can use this to compose more complicated functions by simpler functions. You can do a lot of these convolutional methods that people also sometimes do with neural networks. Then if you actually use as the kernel locality preserving encoding method, the fractional power encoding, then I showed you briefly that with different binding operations, you can map to different neural networks. And then you can kind of shape the kernel by the sampling distribution of the base vectors. I showed you that. And basically what you can implement, of course, is any band limited kernels. So this is the coarse classification of what you can do with it. I showed you briefly that a mechanism for decoding and error correction in VFAs, which is a little bit different from what you usually do, but not much, because you can use actually just these landmark points in a standard associative memory and do the rest just with the FPE circuit. And and finally, this connects to another piece of work that we also discovered when we were in the middle of writing this. And so the problem, so you might wonder, you know, kernel methods became very, very popular in the early 90s after the first disillusion with neural networks, and everything was kernel methods. There was this beautiful theory that people dug out and added to it, and so beautiful Wapnick, Bernhard Schölkop, and so on, very interesting in a way, but nowadays you hear very little of kernel methods, right? And the question is why? And let's see here. Can you still hear me? My connection is apparently a little bit unstable.
Yes, it was some deteriorating quality, but it's okay. It's okay.
Okay. Is it now better?
Yes, we can hear you.
Yeah. Okay. And one of the reasons why kernel methods fell a little bit out of favor is a curse of dimensionality. The problem is if you have learning problems with tons of data points, that in order to apply the kernel trick, you need to form the kernel matrix, which is basically the kernel evaluation for all pairs of data points that you have in the learning problem. And this becomes very unwieldy. And the nice thing is that the VFA encoding, or these kind of randomized feature encodings that are used in VFAs, can actually map the kernel, or can actually compute the kernel by now just mapping into these random features and forming inner products. And then you don't need to keep track of the entire kernel matrix all the time. You can form the kernels that you need on the fly. And so there was by Rahimi and Recht, Recht is in the CS department at UC Berkeley, they pointed out in 2007 already that these implementations of kernel methods might overcome the curse of dimensionality. So it's very interesting that there is this connection now to the VFAs. What is new and what has not been pointed out by Rahimi and Recht is this, that you can actually use the algebra of the VSA, that you actually have a convolution operation and stuff like that. So I think in total, it is a very interesting connection to kernel methods, not only because we can now do what kernel methods do, but also because it's an implementation of kernel methods that overcomes the curse of dimensionality. Okay, so I stop here and leave the rest for questions. Thanks for your attention.
Thank you very much, Fritz, for this exciting talk. So yeah, we have already questions, so let's go. Gregor, you were first, and then Ross.
Just a very general question. So, what in this thinking is there still an idea that this would map onto neurons, onto spiking neurons, or
yeah?
Can you sketch what that would be like?
Yeah, I mean, first to note is that, of course, very mundane neural representations, for example, kind of filter banks with Gaussian receptive fields also actually lead to a kernel LPE. In the case of Gaussian receptive fields, if the neurons are equally spaced and so on, actually this leads to also to a Gaussian shaped kernel function. So this is absolutely, you can think of this also with very common neural encoding circuits. But as I pointed out, you can also really use these different ways to map VSAs and different binding operations using the different representation schemes that I just pointed out in this one slide. But I mean, for example, for the block sparse VSAs, we show in this 21 paper that with this, of course, you are very close to an implementation that you can do with spiking neurons and so on. Another thing to note is also that there's this beautiful link between actually the phasors and actually spike timing representations. This was actually pointed out in a PNAS paper of Parkson and myself in 2019, where we actually showed that you have first these, you can actually build these phasor associative memories that can store continuous valued phase patterns, and how this actually can be mapped onto spiking neurons. So there's quite a bit of connections. And the interesting thing is that it's not only one connection. You can kind of decide what is your binding operation. You know, the Waterloo group used a circular convolution a lot, and also made some, have had some ideas how you can map this with the sparse block binding. But then you also can use standard Gaussian population codes, and you still have VFAs. So I think in that regards, it is pretty general, and you know, can be adapted to many different neural implementations.
Thank you.
Ross, did you have a question?
Yeah, Fritz, looking at applications, I'm interested in Bayesian reasoning, and to do that, I mean, you need to be able to represent distributions. So if you had completely discrete choices with that were not similar to each other at all, and basically you could create the weighted sum of the representations of those different options as your representation of the distribution. So that seems to me like basically you've got a true Kronecker delta function similarity between those, whereas it seems to me that what you're talking about is more appropriate where the options, the parameter space that you're getting the distributions over has, you know, some low dimensional manifold structure to it. So you want, you know, whatever I learn about value, you know, A tells me something about a nearby value of A plus. So you could use the decay of similarity across nearby values to generalize. So effectively your kernel gives you generalization. Could you just sort of speculate on that topic for a little bit for me, please?
Yeah, I mean, this is this kind of this density estimation example. So if you know, Bayesian reasoning, you need to estimate densities, probability densities of different things, and this is exactly why you then need to go from a kind of a Kronecker kernel to actually a similarity preserving encoding scheme, and then if you make sure that this has a kernel, then you basically can use this entire machinery for the Bayesian reasoning. And in a way, it's not unrelated, of course, but it's another proposal how to encode functions and probability densities by vectors to, you know, do belief propagation and all these things that Bayesian reasoning people want to do. I don't know, Ross, that's very brief. Is this?
No, that's fine. I think I just wanted to get confirmation that seemed like a reasonable
yeah, no,
thing
but
to do.
absolutely.
I mean,
yeah.
obviously there's a whole a whole research program involved in actually doing something.
Right. I mean, you know, the other thing is I mean, an interesting question is, of course, you know, how do you, for example, optimize kernels? And I think of this it's almost like a meta learning problem, right? I mean, this is, of course, I mean, if you have some input, you somehow have to ingest the input into your system, and then you can start learning. But if you want to really optimize the input function, then you are really back more to kind of a learning, what I started in the beginning with, right? But I mean, you know, if you're, for example, your sensors, you cannot optimize this way, right? So for our eyes, they have a certain sensitivity in the spectrum and it ends somewhere. I cannot just say, oh, but I really want to see more into the infrared and I need to do that, right? I mean, at some point, your circuitry limits you, and if you want to optimize it, well, evolution can optimize this, but not the individual. So So, but yeah, it's of course an interesting question how, and you can of course optimize then the kernel functions for what you described, right? First you have discrete discrete symbols. You always want to keep them separate. And then you have these things that merge into each other, right? And so you could, of course, you can think about ways to optimize this.
Yeah, if you're doing if you're doing a sort of a classic big data analysis, and you were you had some quantity that you were measuring, but you weren't sure what the appropriate generalization gradient would be over that over the the dimension you were measuring, then presumably you could set up multiple VFAs with different bandwidths of the kernel.
Yeah. Yeah.
And but have those
Yeah.
VFAs be orthogonal to each other, and essentially you'd be looking for a weighted sum of those different representations, which best captured the generalization in the world.
Yeah, that you can do, but then you need to set up these different kernel systems, and you can do that. And this is also how we think right now. I mean, we are thinking about, I talked a lot about this translation transformation, but how do you combine this with rotation and with scaling and so on? And I mean, also in the brain, you see that you have in entorhinal cortex, you have these, actually, as you go through entorhinal cortex, you have actually grids of different sizes. And that might be, this is of course something you could do. It's quite pedestrian because then you need to provide all these different systems that have the different kernels. The question is, could you somehow, on the fly learn one optimal kernel? But it's
well, yeah, I mean, that's interesting because when you were showing the relationships between the phase distributions and the kernels, essentially that seems to be saying that, well, I mean, the phase distribution, if you're talking about spiking neurons, the phase distribution actually encodes the kernel. So, but I mean, the kernel also represents the spiking distribution. So if there's, if there was some way of going backwards to get, the pattern of activity in the system, actually working backwards to modify the distribution of the phase distributions, then that would change the kernels, would it not?
It would, but then of course all your downstream machinery is misaligned, and you would have, so it's, I mean, you can play this game, but it becomes then complicated because if you change on the fly the representation, the basic representations, like the base vectors in the fractional power encoding, I mean, it becomes difficult because the entire downstream then also has to adjust to the new code. I mean, anyway, I mean, there's a lot of interesting questions. Another question is, of course, also, I mean, with this fractional power encoding, the basic element of coding are plane waves, basically. And it's a big, and of course, entorhinal cortex model have had this problem before. We don't see plane wave responses in brains. We see grid cells if one looks closely in an entorhinal cortex, but we don't see plane waves. And plane waves are very, very basic to the FPEs. So why don't we see plane wave responses, right? So if you have a random projection in a plane wave nonlinearity, basically in the neurons, this creates a fractional power encoding of a d-dimensional input, and we don't see those. And the grid cell models, they had the same problem before. They also kind of have these interference models where they kind of these velocity controlled oscillator models, and they carefully avoid in their models plane waves, and then so that immediately the grid cell characteristic emerges. And this is interesting. I mean, it could be that plane waves are very inefficient in terms of sparsity because they have these ridges along which the firing stays just high. If you wander in a plane wave along one of the ridges, activity just stays high. And this might be very inefficient. And so there might be really reasons why the brain does some of these Fourier compositions of more complicated kernels, but avoids somehow the basic element of the plane wave using some nonlinear mechanisms. But it's a good question. I mean,
Okay, thank you.
I have a question on my own, Fritz,
Yeah.
if you permit. I'm trying to reflect that what you said to my specific practical needs, and I was thinking about this, what you said about building a path in this space of fractional encoded vectors. I understand how it works if you have, say, a single base, but I mean, can you probably elaborate if you can define such a path, or your theory can provide some hints on how to define such a path, and say in more complex scenarios, like when you superimpose or you bind two bases, like a plane, for example, or some more complex shapes.
Yeah, I mean, if you just go from 1D to 2D, it's rather simple, because so basically you then have you have kind of you have two phases, and you then again the path then just goes, so you have then also one base. So I mean, remember, the base vector is sampled from a distribution, and depending on what the distribution is, you get different kernel shapes. But you sample, and then you have just these two base vectors, and the path of a 2D is then really just taking each base vector, exponentiating it with one coordinate, and the other you exponentiate with the other coordinate, and you bind. So it's not
this I understand, but if you are given already a composite vector, can you somehow define a path without knowing the to which coordinates it actually belongs? Or
no, you need to know for the decoding. This is like in simple VSAs also, right? You need to know what the codes are. Otherwise, you cannot parse or decode the data structure. There's no way. You need to know the base vectors. So it's exactly the same as in symbolic VSAs. So if I just hand you a vector and say, yeah, this actually encodes a number, that's not good enough for you. You don't know what that number is. You will never find out. But if you have the base vector, you find out.
Okay. All right.
Okay, we are over time. Any other questions?
Well, let's wait for 5 more seconds if anybody wants to ask. Well, if not, then we always have our mailing list. So, or feel free to contact Fritz directly with your questions. So I would like to thank Fritz, first of all, for giving this excellent talk. Thank you all for attending it. So let's end the webinar for now, and we will see each other in 2 weeks' time. Thank you.
Thank you, guys. Yeah.
Bye-bye.
Thank you,
everybody.
Yeah.
Thank you.
Bye-bye.
Bye.